In this video, we're going to continue to talk about how waves interact with one another, how they interfere. So when there's two pulses moving through the same material and they happen to overlap or occupy the same space, we kind of already know basically what happens when there's two pulses that are moving in opposite directions and they happen to occupy the same space, like up here on the left. When they overlap, they add together, or in this case, this is constructive interference, when then they both have an amplitude above equilibrium. If they were both below equilibrium, they would add together and make an even deeper trough. When you have the case of one pulse above equilibrium and another one below equilibrium, they add together destructively. So you could say this has like a negative amplitude, this is a positive amplitude, and if you have the same height but on opposite sides, when added together, you get destructive interference. And here's an example of complete destructive interference, where they have the same height but on opposite sides. And so the material at this location doesn't move from equilibrium. Well, we've already discussed this. So we're going to use these two ideas of constructive and destructive interference to help us understand how a little bit more complicated waves interact, like periodic waves. So let's say we had two people on either side of a slinky or a string, and they shake, one person shakes the left-hand side up and down periodically. The right person does the same. So you would have two periodic waves, one moving from right to left, one moving from left to right. And if that's the same slinky or the same material, those periodic waves are going to pass through one another as if they didn't interact, but the material is going to behave by adding together and subtracting to give us something a little bit different. And so this video is all about thinking through what gets created by the interaction of two periodic waves moving in opposite directions. So in the top of the screen, I have a little simulation to represent just the situation we've been talking about. So on the right-hand side, let's say somebody's shaking the one end back and forth, and the dashed brown line will represent the periodic wave created by the person on the right-hand side that's moving to the left through the material. We're going to call that periodic wave number 2. On the left-hand side, we've got a blue dashed line which represents the periodic wave moving from left to right, moving through the material. These represent the individual pulses moving through there, but if they are in the same material at the same time, like is shown right here, what is the material actually doing? Remember, the material can only do one thing. It can either be at equilibrium, above equilibrium, or below equilibrium. And what determines where it is depends on what part of each wave is at that location at any specific time. So below here, I'm going to show you what the sum of those two waves look like when you add everything together at every point in time and show you what that animation looks like. Now, it does look there's a lot there. It looks a little confusing, so we're going to pick a few specific spots and talk about what's happening there. For instance, let's look at the middle right here. This green line represents the sum of both individual pulses, and that's what the material is actually doing. So the green line represents the sum of the pulses. That also shows us what the material will actually do as a result of the sum of those two things. So if we look in the middle right here, you can see that the material is staying along the equilibrium line. That must mean that's a spot where there's not just destructive interference, but complete destructive interference. That happens when you have one wave that, let's say, has a positive amplitude, another one has a negative amplitude. And if I put the little red dot there and you kind of watch just that spot, you should be able to see that whenever the brown pulse is above equilibrium, the blue pulse is below equilibrium, the same amount, and vice versa. And so the waves always cancel each other out at that location. And if we look over here, here's another spot where they always cancel each other out. And here's a spot, and here's a spot where they always cancel each other out. So those are spots of complete or total destructive interference. Well, let's take this spot right here, where the green line is getting the farthest positively from equilibrium and the farthest negatively from equilibrium. And why is it getting so far from equilibrium? Well, if I leave my little red dot there, you can see that that's about 3 grid spaces above equilibrium. And why does it get like there? Well, notice when it gets the largest positive displacement, that's when both wave pulses where their crests are meeting. And each crest is about 1.5 wavelengths high. Sorry, 1.5 grid spaces high. And so when you add 1.5 and 1.5 together, you get 3, like this. Or if we go, let's say, 3 grid spaces down here, why does it get so low? Why does it have such a large negative displacement from equilibrium? Well, that's the same location where the troughs meet. So where the troughs meet right now, you get maximum negative displacement. Where the crests meet right now, you get maximum positive displacement. And so this shows us not only what the material is doing, but what the individual pulses that are moving through there and interacting or interfering are doing. But if we were just to actually look at the material itself, we would just see what the green line represents. So the material looks like this when the two waves are added together, and constructive and destructive interference at each point in the material gives rise to its overall behavior. And when you have something that looks like this, in physics we call that a standing wave. It's not that it's like standing completely still, but it like the location that stays at equilibrium is staying right there. And the spots in the material that have the largest positive displacement and negative displacement from equilibrium, they're also kind of staying in this left-right location. It doesn't look like anything is moving from right to left or anything is moving through the material from left to right. It appears that way because, well, there are things moving through the material, right? The blue pulse is moving to the right, the brown pulse is moving to the left, but it's just the interference of them that creates something that looks like it's standing still. So this is the big new idea with this video is a standing wave or standing waves. So standing waves are created when two periodic waves move through the same material in opposite directions. And what gets created is the material seems to stand in place. It doesn't seem to be moving along, nothing seems to be moving along the line of the material. Well, we already identified a couple spots that aren't moving from equilibrium. We call those locations nodes. So where the red dots are what we call nodes, and that's locations of total destructive interference where the material stays at the equilibrium position. The spots in between the nodes where the blue vertical lines are represent the spots of maximum positive and negative displacement in a standing wave, and we call those antinodes. So an antinode is a location of maximum constructive interference where the material has the largest displacement from equilibrium. Another thing I want to look at is what's true about the wavelength of the periodic waves that move through here that create the standing wave compared to, let's say, the distance from one node to another node. Well, if we look at this, one wavelength would be like that or like that. That's one wavelength. So from one node to another adjacent node is only half of a wavelength of the periodic wave moving through there. Or if we start at this node, that right there is one full wavelength, and so we have to go from this node all the way over to the second adjacent node to get one full wavelength like this. Let's say you wanted to create a transverse standing wave and it was just you. We didn't have two people to shake both ends of the string or a slinky for periodic waves to like move through one another like we just talked about. Let's say it was only you. You had one end of a string or a slinky attached to something so it couldn't move, so we've got one fixed end on the right, and you just move the slinky back and forth at different frequencies like it's shown here in the simulation. Well, how can you create two different periodic waves that move through one another in opposite directions? Well, think about it. If you shake one end of a string or material, you're introducing periodic waves which moves through the material from left to right. When it hits that fixed end, those periodic waves bounce back and then move from right to left through the material. So if you just keep shaking the left end of this string, you're going to continually produce periodic waves moving to the right, and there's going to be a continual reflection of those periodic pulses moving from the right back to the left. And so you're going to get two periodic waves which move through one another, and they move in opposite directions. And so if you shake one end of a slinky or a string or any material, you could set up a standing wave. So I have a simulation with 4 just different frequencies of disturbance, disturbing it on the left-hand side with 4 different frequencies. And the question is, do any of those frequencies create standing waves in those strings? Well, how do we know if it creates a standing wave? You have to look and see, does the material have nodes, spots where they stay at equilibrium, and antinodes that have a big displacement from equilibrium? Well, looking through those 3 different options, there's only one that actually produces something that resembles a standing wave. If we look at it, it's right here. The frequency of 1.2 hertz creates something that looks like this, and you can see that I've got the 2 nodes locations marked and the antinode locations marked, where there's like spots of maximum displacement that seem to stand still. Actually, we have 3 antinodes, and technically we don't have just 2 nodes, we have 4 nodes, because right here on the fixed end, that's not moving from equilibrium, so that has to be a node. And technically, if we look at the other end, this is the spot where the person is disturbing the material. And so it's technically not still, it's not fixed. But what do you notice about the displacement, the initial disturbance, like the initial amplitude, compared to the maximum amplitude of the standing wave? Well, a small amplitude disturbance at the right frequency will create a very large amplitude standing wave. And so relative to the maximum amplitude here at an antinode, that's more or less staying still. And so whenever we have something like this, we approximate this to be a node. So we say that there's very little displacement from equilibrium. So we have 1, 2, 3, 4 nodes in this case, and 1, 2, 3 antinodes. So in this case, only one of the frequencies that were tried actually creates a standing wave. And this is important. Not all frequencies will create standing waves. So just because you shake something periodically, introduce it with a constant frequency, that's no guarantee that you're going to actually create a standing wave. Only, in this case, only 1.2 hertz created a standing wave. And there are other types of standing waves that can be created, but those will be created by different frequencies. So let's take the case of the standing wave that we found in the previous slide and find out like what's true about that periodic wave, which was actually able to create the standing wave. So let's see if we can figure out what the wavelength of that periodic wave is and how fast are those pulses moving through the string. Well, let's wait to the very beginning of this animation, because I'm going to pause it and we can basically look at that paused right here. So if we look here, that is 1 wavelength and a half a wavelength that gets created by this particular frequency. And so how big is 1 wavelength? Like we saw with the pause simulation, 1 wavelength is this right here. That's 5 centimeters in length. So a wavelength is 5 centimeters. Or the wavelength created that made that standing wave was 5 centimeters. Another way to look at it is to think about how many wavelengths fit in like the full length of the string. In this case, if we look at the meter stick down here, we can see that the length of the string that's used is about 7.5 centimeters. And so we can say the length of the string, which is 7.5 centimeters, is the same as 1.5 wavelengths. So if we have this statement, we can solve for how big a single wavelength is. Lambda here is an unknown. This is an equation. So if we divide each side by 1.5, we end up getting that wavelength is equal to 5 centimeters, like we talked about initially. Well, if we know the frequency of a periodic wave and we know its wavelength, we should be able to calculate how fast those waves are moving inside of the string, because we have an equation that tells us how wavelength, wave speed, and frequency are related. If we know the wavelength and we know the frequency and we're solving for wave speed, which is that v variable, we can multiply each side of this equation by frequency. So it's going to like cancel out on the right-hand side and get put over there on the left-hand side, and we get this. that wave speed is equal to the frequency of a periodic wave multiplied by its wavelength. So the frequency of 1.2 hertz, or remember, a hertz is the same thing as inverse seconds, multiplied by the wavelength, which is 5 centimeters, we end up getting a wave speed, which is 6 centimeters per second. That should actually sound familiar because remember, when we use that simulation, the FET simulation, waves on a string, to look at the relationship between wavelength and frequency, which is the lab we use to come up with this equation, those of you who used the string with high tension, we found out that the pulses or the periodic waves move through that string at 6 centimeters per second. So it's consistent. And that just brings up the point that no matter what you're doing to the string, whether you're creating an individual pulse, a periodic wave which you can see moving through that string, or you make a standing wave like we have in the animation here, all of those things will be moving through at the same speed because tension is really the only thing that determines how fast something travels through a string or material. So here I have the same simulation set up with the same length string, but instead of using 4 random frequencies just to see if it creates a standing wave, I've chosen 4 frequencies that actually create different looking standing waves. So the one down here is the standing wave that we saw before with 4 nodes and 3 antinodes with 1.2 hertz. Well, it turns out that the lowest frequency that can create a standing wave is 0.4 hertz, and the lowest frequency is 0.8 hertz. The next possible frequency is 1.2 hertz, and the next frequency up after that is 1.6 hertz. So let's just think about in general, why is it that this frequency creates a standing wave? Well, if we look at this standing wave, if we wait till the simulation starts over, we can basically find out how much of a wavelength is in that length. So from one end to another end, that's just half of a wavelength. So the 7.5 centimeter length there's only half of a wavelength that fits in there because it needs to be a really large wavelength. So if we solve that for the needed wavelength to create this specific looking standing wave, we need to use a wavelength that's 2 times bigger than the length of the string, which would be 15 centimeters. Well, the next possible standing wave that would be created, how many wavelengths fit in this same 7.5 centimeters of length? Well, when we paused it, this is one wavelength that fits in there. And so the 7.5 centimeters will be equal just to one wavelength. So the wavelength needed to be created is exactly 7.5 centimeters. If you have a string of a given length, then you can create a periodic wave that has the same wavelength as the length of the string, you're going to create a standing wave that looks like this little animation right here. And notice we have how many nodes in this standing wave? Well, we have 1 on either end, and we have 1 in the middle. And we have 2 antinodes. Notice that these 3 nodes here are evenly spaced, and these 2 nodes are evenly spaced. That's one thing we're going to find out in all standing waves. The number of nodes that we have, they're going to be all evenly spaced. We've already talked about this one quite a bit, so I'm just going to go show the numbers. Remember that there's 1.5 wavelengths that fit in this length. So the length is equal to 1.5 wavelengths. So how big of a wavelength do you need to create to make this specific kind of standing wave? Well, solve that for lambda, and you get that the wavelength needs to be 5 centimeters in length. And if we look at the nodes, there's one in the end here, there's another here, there's another there, and another there. Once we let the animation kind of run through a little bit, you can see that these nodes they're 4 evenly spaced nodes. So what's the next possible standing wave? Well, we had 2 nodes evenly spaced, 3 nodes evenly spaced, 4 nodes evenly spaced. The next one will likely have 5 evenly spaced nodes. So we have 1, 2, 3, 4, and 5. That's the case. So how big of a wavelength here is needed to be created? Well, how many waves fit in this length? If we wait till it pauses, right now we can see that there is 2 wavelengths. So this length is equal to 2 times the needed wavelength. If we solve that for the needed wavelength, If two of them fit in the full length, that means the wavelength only needs to be half as long as the string itself. With a 7.5 centimeter string, that's 3.75 centimeters. We could keep going, I won't, but the next possible standing wave would have 6 evenly spaced nodes, and then the next one would be 7 evenly spaced nodes. But what's true about all of them, other than the fact that the nodes are evenly spaced, is you have to have 2 nodes on either end for a string that has 2 fixed ends that has a standing wave inside of it. So the last thing we're going to look at together is just an example problem. What kind of problem could I ask you to solve about standing waves? So let's say we had a slinky or a string, in this case a slinky, attached to a wall. It's a fixed end and you're going to disturb it back and forth. I might ask you, what frequency would you have to disturb this to create not just any standing wave, but a standing wave with 5 nodes? So the question is, with what frequency would you have to disturb a 6 meter long slinky to create a standing wave with 5 nodes? Let's say we also know the waves move at 12 meters per second through the material and the slinky is fixed at one end. So down here I have an animation which shows what that standing wave would look like. It would have 5 nodes. It would have 1 on this end, 2, 3, 4, well, let me let it get going again. So 1, 2, 3, 4, and 5 nodes. So that's 5 nodes and 4 antinodes. It's kind of easy to figure out what it's going to look like if you have an animation, but on a typical problem, you're not going to have an animation to work with. So how do you think this through? Well, if we have 2 fixed ends, one over here, and remember we're imagining where you're shaking it is also acting like a fixed end, there has to be a node there. And we want to create a standing wave not with 2 nodes, we want to create a standing wave with 5 nodes. And so we need to have 5 dots all evenly spaced. So if I want 3 more for a total of 5, we'd have 1 in the middle and then kind of 2 evenly spaced like that. So we have 1, 2, 3, 4, 5 evenly spaced dots. That's where the nodes are going to be. Well, remember when a standing wave is created, the standing wave looks like a sine wave. That's kind of like flip-flopping back and forth vertically, but it doesn't move right there. And so what I'd want you to do is start on one end and then draw a sine curve to go like up to a crest, down to a trough, back to equilibrium, up through a crest, down through a trough, and again back through equilibrium. So if we draw our sine curves like that, we can see that with 5 nodes, we essentially have 2 wavelengths that fit in that length of the string. Well, the other way that I want you to draw a standing wave is, remember, like if we just pick an antinode location right here, it might have like a trough, like a really low negative displacement, but then it's going to flip-flop to positive displacement. It's just going to flip-flop back and forth. And so the way that we can represent on a diagram a standing wave is we could take the sine curve that we've drawn and then invert that vertically. And I just have like a lighter gray line to show what the slinky looks like at another time when the slinky is essentially flip-flopped to the other side when it's going back and forth. Or you could just use like a dashed line to represent that like this. You could also draw little vertical arrows to show where the maximum displacement is from equilibrium. And remember, that's what we call an antinode. So now that we have our diagram drawn correctly, now we can go through and figure out the needed frequency. Well, remember, if we have the correct diagram drawn and we know the length of the material that has the standing wave inside of it, we can figure out how long of a wavelength you need to create with your disturbance to create that specific standing wave. So in this 6 meters, how many wavelengths, whole or partial wavelengths, fit in that 6 meters? Again, you start here, we've got 1 wavelength, exactly 2 wavelengths. So that 6 meter length is equal to 2 times the needed wavelength. And if you solve that for wavelength, we get that the wavelengths need to be 3 meters long. Well, if you know how big of a wavelength you want to create, how do you figure out the frequency? Again, we're going to use our wavelength and frequency equation, which also depends on the wave speed. So we know the wavelength needs to be 3 meters long. The problem said that any pulse that moves through the material will be moving at 12 meters per second, and so we can solve for frequency. Be careful when you guys solve for frequency. You have to multiply by f to get it out of the denominator and then divide by 3 meters. And so when you do those two algebraic steps, you get that the frequency is equal to the wave speed, 12 meters per second, divided by the needed wavelength of 3 meters. Notice the meter units cancel out, and you have 12 divided by 3 or 4. And the units you have left over are 1/seconds or inverse seconds, which is the same thing as a hertz. So if you were to disturb this slinky at 4 cycles per second, or 4 hertz, you would create a wavelength of 3 meters. And if you created a wavelength of 3 meters, you'd be able to fit exactly 2 full wavelengths in this length, and that would create a standing wave with the desired 5 nodes and 4 antinodes.